Welcome to a comprehensive exploration of our interdisciplinary terminological framework, designed to enhance communication and standardize terminology across diverse fields. This framework integrates linguistics, genetics, bioelectric morphogenesis, computing, and engineering. By providing detailed definitions and applications for each term, we aim to foster a unified understanding that transcends traditional disciplinary boundaries. Join us as we delve into the core concepts and practical applications that will shape the future of interdisciplinary collaboration and innovation. Phonogenetics integrates phonetic structures with genetic coding, mapping linguistic phonemes to nucleotide sequences. This allows language encoding and transmission via genetic frameworks, creating a foundational link between language and biology. In bioinformatics, phonogenetics designs genetic sequences that store and retrieve linguistic data, forming morphogenetic language processing systems. This revolutionizes genetic engineering, enabling precise cellular function control through linguistic sequences. A lexogenome is a catalog of linguistic units mapped onto genetic sequences, forming a biological lexicon that enables morphogenetic articulation and bioelectric synthesis. It serves as a bridge between language and genetic expression. In synthetic biology, lexogenomes provide a framework for programming cellular behavior using linguistic commands. This allows for precise genetic modifications, tissue engineering, and the development of bioelectric interfaces that translate linguistic instructions into cellular responses. Using lexogenomes advances our capacity to control and manipulate biological systems with greater precision and predictability, mirroring the structured communication found in linguistic systems. BRP synchronizes cellular bioelectric fields with computational networks, forming a recursive feedback loop for morphogenetic data processing and communication. It establishes a dynamic interplay between biological and computational elements. BRP is used in neural engineering to develop brain-machine interfaces that enable direct communication between neural circuits and computational systems. This enhances prosthetics, neurorehabilitation, and bioelectric data transmission in medical and computational fields. The BRP technology can significantly improve the lives of individuals with neurological disorders, providing new avenues for restoring lost functions and enhancing cognitive abilities through seamless integration with technology. Morphocircuitry refers to bioelectrical circuits engineered to control morphogenesis at the cellular level through recursive electrochemical signaling. These circuits act as guides for cellular differentiation and tissue formation. In tissue engineering, morphocircuitry enables the design of bioelectric scaffolds that guide cellular differentiation and tissue formation. This paves the way for regenerative medicine and biofabrication. Morphocircuitry also facilitates the creation of biohybrid systems that integrate biological and electronic components, offering new possibilities for advanced medical treatments and biointegrated technologies. IsoLexis is a standardized linguistic framework that aligns isotopic sequences with recursive language structures, creating a coherent system for interdisciplinary communication. This ensures clarity and consistency across diverse fields. IsoLexis is applied in quantum computing and molecular engineering, where isotopic labeling is used to encode and transmit data through quantum systems. This ensures precise communication across disciplines such as chemistry, physics, and computational linguistics. By providing a common linguistic ground, IsoLexis reduces ambiguity and enhances collaboration, leading to more effective and efficient interdisciplinary research and development. Neurolexic synthesis is the fusion of neural bioelectric signals with lexicographic systems, enabling direct brain-to-computer communication through recursive linguistic algorithms. It bridges the gap between neural activity and computational language. In neurotechnology, neurolexic synthesis facilitates the development of cognitive prosthetics, enhancing memory, language processing, and cognitive functions through seamless neural computational integration. This advances fields like AI and neurology. This synthesis paves the way for innovative solutions in treating cognitive impairments and enhancing human capabilities through advanced neurocomputational interfaces. The CDCM Linguistic Core is a centralized repository within the Centralized Data Center module that manages, standardizes, and transmits interdisciplinary terminology, ensuring coherent communication across fields. The CDCM Linguistic Core is used in global research networks to standardize terminology across scientific disciplines, enabling seamless data sharing, collaborative research, and integrated system operations. This is particularly vital in large-scale projects like the Human Genome Project and global artificial intelligence networks, where standardized terminology is crucial for effective collaboration and data interpretation. Recursive data splicing is the dynamic merging and updating of terminological data within the CDCM, ensuring real-time synchronization and adaptability across disciplines. In computational biology, this facilitates continuous updating of genetic databases, integrating new discoveries in genomics, proteomics, and bioinformatics. This keeps interdisciplinary research current and accurate, enhancing collaboration. Etymorphogeny is the study of word origins through the lens of biological morphogenesis, tracing how linguistic terms evolve alongside genetic structures. This concept is used in computational linguistics and bioinformatics to develop algorithms analyzing evolutionary relationships between language and genetic sequences, enhancing language modeling, genetic analysis, and interdisciplinary research methodologies. Isoterminology is a nomenclature system that aligns isotopic elements with linguistic terms, creating a unified lexicon for chemistry, physics, and language. In nuclear engineering and quantum chemistry, isoterminology provides a standardized language for describing isotopic interactions, facilitating precise communication in research, materials science, and quantum information processing. Phonetic isotopy refers to the alignment of phonetic variations with isotopic differences, creating a framework for encoding phonetic information through isotopic labeling in molecular structures. In quantum linguistics, phonetic isotopy is used to encode linguistic data in quantum states, facilitating high-fidelity data transmission and storage in quantum computing and molecular communication networks. Genomorphology is the study of genetic structures through the lens of morphological patterns, integrating linguistic morphology with genetic transcription processes. This approach merges genetics and language structure. Genomorphology is applied in bioinformatics to develop algorithms that analyze genetic sequences through morphological frameworks, enhancing genetic editing, transcription analysis, and synthetic biology design. Electrolexis is the integration of electrical signaling with lexical structures, enabling bioelectric communication of linguistic information through neural and computational interfaces. In neural engineering, electrolexis is used to develop brain-machine interfaces that translate electrical neural signals into linguistic data, enhancing communication for individuals with speech impairments and advancing cognitive computing technologies. Morphophonemics refers to the interaction between morphological structures and phonemic variations, creating a dynamic system for encoding and decoding linguistic information. This is vital for language processing. Morphophonemics is utilized in computational linguistics to develop speech recognition and synthesis systems that account for morphological and phonemic variations, improving natural language processing and voice-assisted technologies. Bioelectric morphosyntax is the study of syntactic structures through bioelectric signaling integrating linguistic syntax with morphogenetic processes. It is crucial in understanding cellular communication. In synthetic biology, bioelectric morphosyntax is used to design genetic circuits that follow syntactic rules, enabling precise control of gene expression and cellular behavior in biofabrication and tissue engineering. Quantum lexicography is the creation and analysis of linguistic systems through quantum computational models, integrating lexical structures with quantum algorithms. Quantum models enhance language processing. Quantum lexicography is applied in quantum computing to develop linguistic algorithms for quantum data processing, enhancing machine translation, semantic analysis, and information retrieval in quantum systems. Neurogenetic lexis refers to the integration of neural and genetic information within a unified linguistic framework, enabling the encoding of neural signals through genetic sequences. In neurogenetics, neurogenetic lexis is used to develop neural implants that encode and transmit neural data through genetic channels, enhancing brain-machine communication and neural data storage. Isomorphic linguistics is the study of structural similarities between linguistic systems and isomorphic patterns in biology, chemistry, and physics. This facilitates cross-disciplinary communication and innovation. Isomorphic linguistics is used in interdisciplinary research to develop models that map linguistic structures onto molecular and atomic frameworks, facilitating cross-disciplinary communication and innovation in materials science, genetics, and computational linguistics. Recursive biosemantics analyzes biological meaning through recursive linguistic processes, integrating biosemantics with recursive algorithms. In computational biology, it develops models to analyze biological data through semantic frameworks, enhancing genomic annotation, protein interaction analysis, and biological data mining. Linguistic nanotopology studies linguistic structures at the nanoscale, integrating linguistic topology with nanotechnology. In nanotechnology, it designs nanoscale communication systems that encode and transmit linguistic data, enhancing nanoscale data storage, molecular communication, and nanorobotic language processing. Bioelectric resonance synchronizes biological and linguistic frequencies, enabling coherent bioelectric communication through lexical structures. In bioengineering, it develops bioelectric interfaces that communicate cellular instructions using linguistic algorithms, enhancing tissue regeneration, cellular reprogramming, and biocomputing systems. Genophonetics studies the phonetic representation of genetic sequences, creating a system where genetic codes are expressed through phonetic patterns. In genetic engineering, genophonetics enables the development of genetic sequences that can be audibly analyzed and manipulated, facilitating auditory-based genomic analysis and real-time genetic editing. Electrosemantic dynamics refers to the interaction of electrical signals with semantic structures, enabling dynamic communication of meaning through electrochemical channels. Electrosemantic dynamics is used in neural interfaces to transmit semantic data through bioelectric signals, enhancing brain-machine communication and cognitive data processing in neuroprosthetics and AI systems. Morphogenetic syntax is the arrangement of genetic and morphological elements in a structured sequence mirroring linguistic syntax in biological systems. Morphogenetic syntax is applied in synthetic biology to design genetic circuits that follow syntactic rules, enabling precise control of cellular functions and biofabrication processes. Quantum phonology is the analysis of phonological structures through quantum models, integrating sound patterns with quantum state dynamics. Quantum phonology is used in quantum computing for phonetic data processing, developing quantum algorithms for speech recognition, language modeling, and audio-based quantum communication. Neurolexic morphogenesis is the process of shaping neural structures through lexical frameworks integrating linguistic elements into neural development. In neuroengineering, neurolexic morphogenesis is used to design neural implants that influence brain development through linguistic stimuli, enhancing cognitive therapies and neural rehabilitation techniques. Isotopic linguistic encoding is the representation of linguistic data through isotopic variations, creating a molecular system for language storage and transmission. Isotopic linguistic encoding is applied in molecular computing to store and retrieve linguistic data using isotopic markers, enhancing data storage capacity and security in nanotechnology and quantum systems. Recursive bioacoustics is the analysis of biological sound patterns through recursive algorithms integrating bioacoustics with linguistic recursion. Recursive bioacoustics is used in bioinformatics to develop models that analyze biological sounds, such as heartbeats, and neural signals through linguistic frameworks, enhancing diagnostic tools and bioacoustic data analysis. Linguistic electromorphology is the study of morphological structures through electromagnetic fields, integrating linguistic morphology with electromagnetic dynamics. In electromagnetic engineering, linguistic electromorphology is used to design communication systems that encode morphological data in electromagnetic signals, improving wireless communication and data transmission technologies. Bioelectric semantic splicing fuses semantic elements through bioelectric signals, enabling dynamic semantic manipulation in biological systems. Applied in gene editing, it integrates semantic data into genetic sequences, enhancing gene expression control and synthetic biology design, revolutionizing how we control biological processes with linguistic insights. Lexosome refers to a bioelectric unit of meaning encoded within cellular structures, analogous to lexical units in linguistics. In cellular bioengineering, lexosomes encode and transmit genetic instructions through bioelectric signals, facilitating precise cellular manipulation for tissue engineering and regenerative therapies. Phononucleotides are nucleotide sequences sonically mapped to phonetic elements, enabling the auditory representation and analysis of genetic codes. Employed in genomics to develop audio-based sequencing tools, allowing researchers to listen to genetic sequences for error detection, mutation analysis, and structural mapping, providing auditory dimensions to genomics. Morphogenetic lexicon is a structured set of genetic instructions that guide cellular morphogenesis through linguistic principles. This lexicon is used in developmental biology to program cellular differentiation and tissue formation, aiding in organogenesis and complex tissue assembly in synthetic biology, offering new possibilities in regenerative medicine. Quantum semantics refers to the encoding and interpretation of meaning through quantum states, and interactions integrating semantic structures with quantum mechanics. Quantum semantics is utilized in quantum information theory to develop semantic-based quantum algorithms, enhancing natural language processing, machine learning, and cryptographic systems. Neurophonic encoding is the representation of phonetic data through neural signals, creating a direct interface between neural circuits and phonological structures. Neurophonic encoding is applied in neuroprosthetics to enable speech synthesis and recognition through neural implants, providing communication solutions for individuals with speech impairments. Isotopic morphogenetics is the study of morphogenetic processes through isotopic labeling, integrating isotopic variations with cellular development, providing insight into developmental processes. In molecular biology, isotopic morphogenetics is used to trace cellular development and differentiation, enhancing studies in developmental biology, stem cell research, and genetic lineage mapping. Recursive linguistic topology is the study of topological structures in linguistic systems through recursive processes, analyzing the spatial arrangement of linguistic elements. This field is applied in computational linguistics to develop spatial models of language processing, enhancing machine translation, semantic analysis, and language learning systems. Bioelectric phonology is the analysis of phonological structures through bioelectric signals integrating phonetic patterns with cellular electrical activity. Bioelectric phonology is used in neurobiology to study neural speech processing, aiding in the development of brain-computer interfaces for speech synthesis and auditory signal processing. Semantic isotopy refers to the alignment of semantic structures with isotopic distributions, creating a molecular framework for meaning representation. In chemical informatics, semantic isotopy is employed to encode chemical data through semantic frameworks, enhancing molecular design, drug development, and chemical communication systems. Morphophonetic synthesis is the integration of morphological and phonetic structures into a unified system, enabling dynamic linguistic manipulation. Morphophonetic synthesis is used in speech technology to develop advanced speech synthesis systems that account for morphological variations, improving text-to-speech systems and voice-assisted applications. Lexicochemical synthesis integrates chemical bonding patterns with linguistic structures, enabling chemical lexicons for molecular design. In chemical engineering, it designs molecular compounds through linguistic algorithms, enhancing precision in drug development, materials science, and nanochemistry. Phonosemantic entanglement refers to the quantum entanglement of phonetic and semantic elements, creating interconnected linguistic states across quantum systems. This concept is applied in quantum communication to develop entangled linguistic channels, allowing for instantaneous semantic data exchange in quantum networks and distributed computing systems. Neuroisotopic resonance synchronizes neural activity with isotopic oscillations, facilitating bioelectric communication through isotopic signals. In neuroengineering, it is used to develop neural implants enhancing cognitive functions through isotopic modulation. A morphogenetic syntax tree is a hierarchical representation of genetic instructions that mirrors linguistic syntax trees, guiding cellular development. This structure is used in synthetic biology to design gene regulatory networks, enabling precise genetic programming for tissue engineering, developmental biology, and biocomputing. Quantum biolexis refers to the integration of biological lexicons with quantum computing systems, creating quantum biological hybrid communication frameworks. Quantum biolexis is applied in bioinformatics to develop quantum algorithms for genomic data processing, enhancing genetic analysis, protein folding simulations, and bioelectric modeling. Electromorphogenetic linguistics is the study of linguistic structures through electromagnetic fields, integrating morphogenetic signals with linguistic frameworks. This field is used in electromagnetic engineering to develop wireless communication systems that encode linguistic data through morphogenetic signals, improving signal processing, data transmission, and wireless communication technologies. Recursive semantic morphology is the iterative analysis of morphological structures through semantic recursion, enabling dynamic linguistic manipulation. In computational linguistics, recursive semantic morphology is used to develop natural language processing algorithms that adapt to contextual changes, enhancing machine translation, semantic analysis, and text generation systems. Bioelectronic syntax encoding refers to the integration of electronic data, encoding with linguistic syntax, creating bioelectronic communication protocols. This encoding is used in bioelectronic devices to transmit genetic and linguistic data simultaneously, enhancing biomedical implants, biosensors, and bioelectric data networks. Isotopic lexicography is the creation of lexical databases through isotopic labeling, enabling molecular-level language representation. Isotopic lexicography is applied in chemical informatics to develop molecular dictionaries, facilitating precise chemical communication, molecular design, and materials synthesis. Neurophonetic morphogenesis is the shaping of neural circuits through phonetic stimuli, integrating phonology with neural development. This concept is used in neurolinguistics to develop speech therapy techniques, neural rehabilitation protocols, and brain-computer interfaces that utilize phonetic stimuli for neural plasticity enhancement. The framework integrates linguistics, genetics, and bioengineering. It enhances biocommunication and data processing. It provides a unified system for interdisciplinary dialogue. Standardized terminology reduces ambiguity and enhances clarity. Cross-disciplinary collaboration fosters new discoveries and applications. Improved diagnostics and personalized medicine. Advanced biocomputing and data storage solutions. Seamless data sharing and collaborative studies. Ensuring compatibility and accessibility across diverse data sets, developing universally accepted terminological standards. Data standardization, training programs, collaborative projects. Contribute. Share your expertise and insights to enhance the framework. Collaborate. Engage in joint projects to validate and refine the terminology. Access comprehensive terminological datasets. Utilize guides and tutorials for implementation. Accelerated discoveries through unified communication, enhanced global research networks, deeper insights into complex systems. We extend our gratitude to all contributors and partners who have supported the development of this interdisciplinary terminological framework. Your expertise and collaboration are invaluable in shaping the future of interdisciplinary research and communication. Together, we can unlock new potentials and drive innovation across fields. Thank you for joining us on this